Okay, and switch my screen. Okay, can you see it? My computer is a little slow today. I keep turning on for several days, so it's a little bit slow. Just make sure you can see my screen, right? Chapter 5. Can you see clearly my writing on the screen?
Yes, sir.
Okay. Okay, chapter 5, the principle of convection. Okay. So, well, this class used to be a, fluid mechanics 311 used to be the prerequisite of this class, which I feel it's more suitable. Okay, now it's a co-requisite, so it's kind of like you take at the same time. But actually, convection, the flow fluid mechanics on the convection problem is fairly complicated. You know, we usually won't teach until in the fluids class, won't teach until the almost end of the semester. Okay, boundary layer flow, something like that. Pipe flow we did teach a little bit early, but most of you in the fluids class, we haven't reached pipe flow yet, right? So now it seems like we have to teach this in heat transfer class, but that's okay. It's okay. We learn 2 times, right? Usually, yeah, I think the rule of thumb is that when you learn the subject 3 times, maybe you fully understand it. So don't worry, don't feel bad if you not fully understand some of the knowledge. It's okay. Okay, we keep repeating. Yeah, that's actually an honest assessment from my experience. I studied those topics in undergraduate. Okay, so after my undergraduate, basically half a year after that, I mostly forget about everything. Okay, so I went to graduate school, master's. I studied those topics 2nd time. I have a better understanding actually. Then when I got to PhD, study the 3rd time. Now I fully understand. Then I can teach. Okay, so 3 times is the magic number. Okay, so the first type is flat surface. Okay, boundary layer. Boundary, LAYER, boundary layer flow and heat transfer. Okay, I'm not exactly following the order of the textbook. Okay, so I pick some I feel important for you to know. Okay, so what is the boundary layer? What does it look like? Okay, so let's say this is a flat surface. Okay, boundary layer flow means this. Okay, you have a main flow enter the flat surface. Okay, so before it's a uniform flow before you reach that surface. Okay, now you see that surface, you go over it, right? Well, the first surface, of course, like you have temperature heated. Okay, so that will be heat transfer in the flow on top of it. But first, we need to know what does the flow look like. Okay. Okay, any arbitrary location you will see if you try to draw a velocity profile. Now you know the vector, right? In fluids class, you learn the vector. So velocity, we use vector to represent it. Okay, what does the vector field looks like? Okay, arrows. Okay, notice, interestingly, there's a portion when it's very far away from the plate. Sure, then the flow doesn't feel the plate whatsoever if it's very far away. So the velocity at the very far away from the plate is just like a free stream velocity. Let's say U infinite. It's a free 1D problem. Okay, it's just the flow over the plate. So at the very far away to the plate, it's again still the free stream velocity U infinite. Okay. You don't feel the plate basically if it's very far away, okay? But when it's very close to the plate, obviously you feel the presence of the plate, right? Because we're dealing with viscous fluid, so you have viscous effect. So they call non-slip boundary condition. Usually, when the fluid reach to a surface, it stick with the surface Okay, exactly on the surface, actually, there's no flow. Okay, you see, look at the flow distribution. We talk about this in our what, in the viscosity. When we talk about the viscosity, remember, we use this example, right? So when exactly on the boundary, there's no velocity, but when it's very far away from the boundary, there's a free stream velocity. Okay, so in between, there will be a gradual change. Is that right? Is that a gradual change? Just like this, I draw like this, okay? So when it's very far away, you don't feel it, okay? So that's what they look like. Okay, but you wanna set a boundary here. So on a certain point, at a certain distance, the definition is this. So you have a defect region near the boundary. Velocity is smaller than the free stream velocity. Then outside this region, the velocity is the same as the free stream velocity. The region look like this. Okay, so this region under this borderline, this curve I draw here is called the boundary layer border. Okay, so you see the difference, right? So under this border, the velocity is smaller. Okay, and above this borderline, the velocity is the same as the free stream velocity. Okay, that makes sense, right? We separate them with smaller velocity and the normal velocity. So it seems like the boundary layer thickness going to increase when the flow goes through further down on the plate. So at the beginning, it seems like here, the velocity defect area is smaller. Okay, the drawing, bear with my drawing, you can see that clearly, but do you understand what I'm talking about here? So the defect region, velocity reduced region, okay, near the wall region is gradually increased. So the definition of the boundary layer is U over U infinite less than 1%, 99%. Okay. So this is the definition. Okay. If the velocity is less than 99% of the free stream velocity, that region, okay, inside this region, the velocity all smaller than 99%. Why is 99% the magic number? 1% negligible. In engineering, less than 1% negligible. Okay. So you're smaller than 99% of the free stream velocity. It's not negligible. It seems like you reduce a little bit, right? Comparing to the free stream velocity. So that's the definition of the boundary layer. Okay. Okay, but the shape doesn't look like this. Actually, in the tip, when you just enter it, you see the boundary layer is start to grow. It grows, okay, when along the plate. Okay, at the beginning, you suddenly that flow coming in. Of course, everything is still free stream velocity. It's not developed yet, the boundary layer. Okay, then gradually the boundary layer getting, the viscous effect extended more and more and more. Okay, so that's what it does it look like. This is the flow boundary. Actually, they're the thermal boundary. We're going to talk about it a little bit later. Let me introduce the flow boundary layer first. Okay, so the ideal condition is in the velocity defect area inside the boundary layer, the velocity is still 1D, it's still U velocity. There's no V velocity. V velocity, of course, there's still a little bit V velocity, but it's very small, okay, negligible. Okay, so that's the ideal case. Okay, only U. So it's kind of like still 1D problem in the practical application. Okay, so don't worry about the V. Okay, you know what V is, right? Vertical velocity. Okay, so here every vector I draw is just parallel to the wall. Okay, to the surface. Okay, so still 1D problem. It's okay, huh? Okay. Any question? If you have, you can jump in. Okay, let's look at what the shear stress look like. sometimes we want to know the shear stress, right? Okay. Shear stress is from what? In fluid, we know shear stress is du dy times viscosity. Okay. So, okay, so it depends on the velocity gradient. I mean the shear stress on the wall. Okay. So look at the shape of the boundary layer. Because the boundary layer thickness increases, right? The region depth increases. So the profile gradually change, become more gradual when how to say, when x direction x increases, okay. Further along the plate, the velocity profile look like more gradual change. If it's gradual change, the du dy getting smaller, right? The velocity gradient at the beginning, the tip, it's a sudden change. You know, immediately on the surface is 0, but immediately outside the surface is just free stream velocity. It's a big velocity and suddenly becomes 0. So you have a sudden change at the beginning. So your du dy at the beginning of the tip is very big, almost infinitely big. Okay, very big. So this is shear stress versus, no, I'm sorry, shear stress is the y-axis versus x. Okay. So this is what shear stress look like. When you talk about heat transfer, you always want to immediately talk about the shear stress. You know why? Because heat transfer always heat exchanger, heat transfer design. You want to enhance the heat transfer, right? Usually, as long as you enhance the heat transfer, you increase the shear. Okay, so you have a bigger pressure drop. Okay, you know, pressure drop is not good, right? Do you know that? You know, use most of the engineering application, for example, in a pipe flow. You know, in heat exchanger, you want to enhance the heat transfer from the pipe to the flow. Okay, so usually when we enhance the heat transfer, automatically the shear stress will increase. Okay, shear stress will be related to the pressure drop. You know why pressure drop is bad? It increase the pressure drop. The pressure drop is the money. Okay, you want to make the flow, right? Make the liquid flow. You need a pump to drive the flow. Okay, the pump is to overcome the pressure drop in the flow, right? So the more pressure drop you have in the flow, you need a more powerful pump. You know, it's more expensive, kind of like that. So usually it's a train, okay, between the heat transfer and the shear. Okay, heat transfer increases. Usually, for example, you put a fin on it. You put the thing on the surface. Hey, heat transfer increase, but that's the cost. You're gonna spend more money because heat transfer increase. You have a thing. Your thing will cause more shear. You know, more resistance, and they give you more pressure drop along the flow. Okay, so which is you're gonna pay for it. You know, eventually, if you're gonna pay for the pump, and you need to pay for the power, electricity, everything. You know, in engineering, everything is the money dictated, right? Budget. That's budget-oriented design. You know, it's not really what you want to design. It's not garage engineering. Real engineering is everything. You have to look at the cost. Okay, so that's difference, right? So that's why we need to look at the shear. Okay, sometimes you enhance heat transfer. You want to minimize the shear, so that would be good. That would be efficient design. Then you can have less cost. Okay. So the shear stress along the plate will look like that. It's actually in the beginning, and the tip is very big. Based on this equation, you know it's very big at the beginning, but it will gradually decrease because the du dy becomes smaller along the plate on the x direction because the profile become more gradual later in the flow. Okay, later on the plate. So the shear decreases like this. Okay. So this is laminar flow. Okay, seems like very regular. So that's what we call laminar flow. Did we talk about laminar and the turbulent flow in the beginning of the fluids class? We talked about it, right? Remember?
I think we did.
Yeah. Turbulent is more like chaotic. It's hard to describe, and the chaotic means it changes every time. Every time you look at it, there's no rule, no regulation to guide the turbulence, right? It will be turbulent. So every time you look at it, it will be different. So it's difficult to study. There's no theoretical equation, for turbulent flow usually. But this is laminar. You look more regular. Actually, if you look into the textbook, maybe usually they cover in the graduate fluid mechanics. Okay, so they would derive, actually analytically solve the problem for this laminar boundary layer flow as well as the heat transfer. Okay, here we don't need to worry about the theoretical part. But that's what the laminar look like. Okay. Okay. Then, if the plate is very, very long, what happens? It seems like the boundary layer thickness keep increasing. Okay, my drawing is not that good, but actually in the laminar region, it is keep increasing. Okay, will it increase to infinitely thick, a boundary layer? If the plate is really, 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 really long, I don't think so, right? Nothing really in reality will be infinite. Okay, it will increase a little bit but until for certain lengths of the pipe, until reach to that, then the boundary layer flow become turbulent. Turbulent means very, very chaotic, small eddies. It's no longer 1D straight flow anymore. It becomes circulation, vortices, eddies, whatever you want to call it, right? It becomes so complicated. Okay, so that's what happens. If the plate is long, then gradually, okay, the boundary layer flow become more chaotic, become turbulent boundary layer. Okay, so along the same location here, the shear gonna change significantly. It will suddenly increase, then gradually decrease. Okay, it's entrance region. Well, it's not, it's a transition region. Okay, suddenly it will increase the shear a little bit when it start the transition. Then actually at the end, it start to decrease also. Okay, if it's further longer. Okay, so that's a behavior of the shear stress and the flow along a flat surface, okay, with flow passing it. Okay. So then I think now obviously you know, how long that would be the point. I need to know, because when I design some heat transfer surfaces, I need to know where the flow starts getting turbulent. Because sometimes turbulent is good. Look at the shear stress. If a turbulent flow at the beginning increase, the shear stress increase a little bit, but if it's further long, very, very long, the shear stress actually decreases. Okay, it's smaller than the laminar shear stress. Okay, so maybe for some design, you want the plate, you want your heat transfer going to long enough so that the heat transfer will be in the turbulent boundary layer, because the shear is smaller. So for the design, hey, that's good, right? You want to increase, probably heat transfer is still similar, but your shear is decreased. Okay, so that's probably a good thing for the design, turbulent boundary layer, right? Okay. Now, there's an example, for this turbulent and laminar flow. Why turbulent is better? Do you guys play golf? Any of you in the golf team or whatever, McNeese golf team? No? But probably some of you do play golf, right? But I guess golf is probably a little bit older people's sports, I guess. I don't know. Okay, but whatever. Did you guys see the golf ball? The golf ball has a dimple on it, right? Right? Is that right? Golf ball. You see golf ball before, right? I don't have one in here. So why there's a dimple on the golf ball? Why not the golf ball is just like a smooth, like a ping pong ball shaped golf ball?
It's for air current.
Yeah, it's for the flow. Now you know. I'm talking about this in this class. It must be related to the flow, right? So why a golf ball? Actually, 300 years ago, the old Scottish, when they play golf, the ball, indeed, it is a smooth ball. The dimple is a new thing. It's not original. Okay, but it is. And then they noticed when the ball getting older, the ball getting very old and very non-smooth, then it seems like they hit the ball further. Okay, they noticed that. Okay, then so hey, why not we make the ball not smooth, with roughness on it, Then the ball seems like with the same strength, I hit the ball further. Okay, so actually that's true. That's true, because if you put the golf ball in the wind tunnel, you do the test, you will see actually dimpled golf ball has less drag than the smooth golf ball. Okay. Okay, it does have less drag. But why there's less drag for the dimpled golf ball? That's because of this. Drag is based on it comes from the shear, right? Especially in the aerodynamics, totally it's from the shear. Okay, so although the golf ball surface is not a flat surface, but they share the same reason. Okay, when you have a dimpled golf ball, then actually the flow around the golf ball when it flies, when the flow around the golf ball is more turbulent than a smooth golf ball. Okay, it actually is more turbulent. Turbulent give you small eddies. Instead of a laminar flow, you have bigger vortex in the wake, okay, which will lead to more drag, okay, more shear, okay. And the small turbulence, turbulence, the size of the turbulent eddy is basically dictated by the structures, the dimples, So the size of those turbulent eddy is very small, okay. So the drag actually have a lot of vortices, but with smaller strengths. Okay, with a small ball, you will see a too big vortex in the wake of the flying small golf ball, but it's very big drag. But the smaller breaked up vortices actually has smaller shear and the smaller drags. Okay, but that's a different. That's just an example. So why it's longer when the flat plate become longer, then the laminar flow cannot be held anymore, then become turbulent, and the eddies start to generate, turbulent. Then the shear stress actually eventually decreases comparing to the laminar region. Okay, so that's something you probably want to remember when you do some design, surface design for heat transfer. Maybe what people do is put a trip wire in the tip of the surface, so to minimize the laminar boundary layer region. You have the trip wire in the tip, then what happened? The turbulence immediately started from the trip wire. So that's a trick, for the design. So it will be onset of the turbulence from the beginning. So then the shear will be smaller. Okay. So these are important things for the design. Okay. When you do practical design, you really have to be knowledgeable. Okay. So to guide your design process. Okay. So then the next question is where this point is. It's important to know where the point is. Okay, so if your plate is very, very long, okay, it doesn't matter. My laminar region is only just 1/10 of it, so it doesn't matter. Most of my region are turbulent, so my shear should be good, and my drag should be small. Okay, but if your plate is just half laminar, half turbulent, then I guess you probably want to do something to set the onset of turbulence earlier, because the laminar region is too long, in your plate. Then you have a lot of drag, a lot of shear. Okay, so we want to know where this is. We use something called Reynolds number. Okay, but this Reynolds number is different comparing to the Reynolds number in pipe. Remember, Reynolds number in pipe. Reynolds number is always what? Velocity times a length scale, then divided by the kinematic viscosity, right? That's Reynolds number. Many of you already did my fluids. You probably know this. If you don't, that's what Reynolds number definition is. It's a velocity times a length scale. In this case, you don't have a diameter. In pipe, it's just times the diameter of the pipe. That's your length, right? But here, what is the length? It's the x, the distance along the plate, divided by viscosity. The velocity I use, the characteristic velocity, which I cannot use there's many different velocities in the boundary layer, right? So which one I use? So I don't want to use those, change the velocity. I want to just use the free stream velocity to characterize my flow, my Reynolds number. Okay, so this is the definition for Reynolds number. It's to describe actually how fast the flow is, how big the flow is, how sticky the flow is. You know, you see the viscosity is down here, right? Nu, you know, you still remember nu, right? Viscosity. So this Reynolds number, if the bigger the Reynolds number is, it means usually relatively faster flow, bigger flow, and less viscous. Okay. If the Reynolds number is small, then in other way, it seems like a very slow flow in the very small scale, very viscous, very sticky. Okay, so from looking at the number, the Reynolds number, you can tell the characteristic of the flow a little bit. Okay, so you see, this is Reynolds number is not a certain number. It's not like in the pipe. Each pipe flow you have a Reynolds number because there's a diameter that doesn't change, right? Here, which means that at every location on the plate, on every different x, okay, you will have a Reynolds number. Okay, you will have a Reynolds number. So for this point, you know, at the beginning point, your Reynolds number is really small. Well, that makes sense. In the beginning, actually, it's very viscous. See, that region is small. Okay, and then gradually, and different locations along the plate, later locations, then you have a higher Reynolds number. Okay, so in this point, the critical Reynolds number for, let's say, critical between laminar and the turbulent flow is 5 by 10 to the 5. Okay, so that's the critical magic number. I think it's what, 500,000? 5 by 10, 50, right? Is that 500,000? Yeah, 60 is like a million, right? So it's 500,000. Okay, so 500,000 is the critical Reynolds number. Indicate that X location. That location is that the location separate the laminar and the turbulent boundary layer. Okay. Does that make sense? This is kind of like a strange when you listen hear it first, because people usually used to the Reynolds number for the pipe flow. Hey, come on, each pipe has one Reynolds number, right? So now you have so many Reynolds number, each Reynolds number representing a location, okay? Representing a Reynolds number on a certain location, okay? So when you reach to this location, your Reynolds number will be 5 times 10 to the 5. Okay, so I can come back to ask you. So I give you a plate, a situation. So you can actually calculate where is the transition happens, right? Because that 5 by 10, 5 is a certain number. So you can back calculate that X, critical X. So you know where is your transition location between laminar and the turbulent. Okay, does that make sense? Well, these are all new to you, right? These are the new information. So let me know if you have any questions on this. Okay, so but you need to remember this Reynolds number. Okay, I want you to remember this Reynolds number. Okay, so then I will talk about, it will have a turbulent boundary layer. It's a different boundary layer. It's not identical to the laminar, but let's wait a little bit. Let me introduce the conduit, okay, pipe flow also. Laminar, this is laminar boundary layer, turbulent boundary layer, right? For the plate surface. So next topic, let me give you an introduction on the boundary layer for the pipe flow, for the in the tube. Okay. Boundary layer flow. Okay. What does it look like? Now we're dealing with the pipes, okay? A lot of times we probably gonna look at the cylindrical coordinate, okay, unfortunately, all right? So pipe, okay, what does the entrance look like? So let's say we have a circular pipe, right? Okay. So in the beginning, before you enter the pipe, the flow is also straight flow, simple 1D problem, okay? limited to 1D problem, otherwise it's too complicated. Okay, but it's straight flow and the uniform flow. Okay, it's before you enter the pipe. Okay, so what happens after you enter the pipe? It will be a gradual change. Again, just like the boundary layer, flat surface. At the beginning, it changed just a little bit because it just entered it. It don't feel that pipe yet, not fully developed yet. Only the region very close to the wall has some reduction of velocity. Okay, gradually along the pipe, then it become more parabolic. Did you see the change from the entrance to later part of the pipe? The shape of the velocity changes, right? The shape of the velocity profile changes, okay? It changes from here to here, okay? So, but what happened when the pipe is very long? It's not like it's not like in the surface flat surface boundary layer problem. It seems like become turbulent. Right? No, in the pipe flow, it doesn't change. The turbulent or not dictated by just the Reynolds number you have, but it's nothing to do with along the pipe bone. If it's turbulent from the beginning. Okay, so but if the pipe is long enough, gradually it becomes non-change. So in the beginning, it's a developing region, entrance, or developing region. Okay, when you reach to a certain length here, it becomes fully developed. Okay, so that's what happens inside the pipe. Okay, is that right? Does that make sense? Okay, so what does the boundary layer look like? You also have bad drawing. Okay, let me erase it. Okay. Okay, there are also a boundary layer. Start from beginning. Shape similar to the flat plate problem. Okay, for all the surfaces, right? The same profile, gradually increase. But will it continue increasing? I don't think so, because when you reach to the fully developed region, the velocity profile doesn't change anymore. In that sense, your boundary layer doesn't change anymore. It becomes a straight line. At the end. It won't turn to turbulent boundary layer. It will just be like that. But if the flow, initially it is a turbulent pipe flow, then the boundary layer will be turbulent pipe boundary layer from the beginning. Okay, so that's a difference. Okay, in some problem, that two boundary layer will meet. If the pipe is not very big in diameter, then the two layer will meet. Okay, meet in the middle. It's possible. Okay, it's possible. Okay, again, what is the definition of the boundary layer border? Do you still remember? 99%, right? Remember? 99% for the free stream velocity. Okay, so 99% of the velocity, it doesn't change anymore, right? So if the profile, the fully developed profile is you have a region in the middle doesn't change much, pretty flat, then your boundary layer, you're sure they're not meeting, okay, for all different surfaces. Okay, but if your profile is like a develop profile just like this, you see, it keep changing, right? To the maximum, it's keep changing. Then I think likely your boundary layer will meet, okay, like that. Okay, so this is a laminar pipe flow. And turbulent pipe flow, it look very different. Okay, turbulent pipe flow, it's like this. So it won't have a parabolic shape, okay? But actually every time when you look at it, the fully developed region is always like this. It's chaotic. Okay, this is one, maybe a snapshot I take at 8 o'clock. When I take it at 9 o'clock, it will be different. Take at 8:01, it will be different. Okay, but it will be like this. It oscillates. It's a different oscillation, different fluctuation, basically. But overall, it just look like this, right? But it's all different. Every time is different, chaotic, right? It's turbulent. So, but if you take time average, you will see a kind of a profile like this, averaged velocity profile. Okay, if you average out those fluctuations over time, then it becomes just straight line, right? See, it fluctuates about a mean value. So this is, if you average it for a long period of time for this velocity profile, it will become like this. Don't worry about their fluctuation. Okay, usually we'll care about in engineering application, we only care about the mean flow. Okay, mean velocity or mean flow, mean speed, or whatever, right? We don't care about the fluctuation time to time. If you average out, it's just like this. Okay, so, well, actually, if you look at the average velocity, you probably like to deal with turbulent pipe flow, right? It looks like a straight line here. Like a velocity is like a constant. Although there's a region up and down, seems like a velocity is smaller, but most of the place, it seems like it's a uniform velocity. If you just look at the average mean velocity, okay? So it's kind of like a good. So calculation-wise, if you will only deal with the mean velocity, time average the velocity, then actually the problem is simple. We just usually use that velocity as average velocity, basically. Okay, and also the developing region for turbulent flow is sometimes smaller, okay, than the laminar boundary layer, and then fully developed. And the average mean profile, it doesn't change inside the fully developed region. And the boundary layer, obviously, you see, it's smaller boundary layer, okay, it's smaller if you draw the boundary layer, because boundary layer only ended up at the place, then it stopped the change, velocity stopped the change, stop changes. Okay, so the boundary layer seems like smaller. You know, smaller boundary layer is good, right? Boundary layer is not good because boundary layer has velocity defect reduction inside, and it has a stronger viscous effect, and it will be leading to shear, right? Turbulent boundary layer is better because it's thinner. Okay, also it's thinner. So that's what the flow field look like. Okay, so this two type of problem that we're going to deal with. So we're going to deal with heat transfer. If the flat plate is heated, so how the heat transfer following the flow, and if the pipe wall is heated, and how the heat transferred inside the pipe flow. Okay, these are our future goals. Okay, but here we need to understand what the flow look like before we continue on the heat transfer part. Is that okay? I spent this class 40 minutes, you know, cover the material, maybe try to cover in fluids, you know, many classes. Okay, so I just want to give you a brief introduction. Okay, don't have time on many details. So the Reynolds number for the pipe flow is easy. Velocity, also the inlet velocity times the diameter divided by viscosity. Okay, you probably need to, if you can remember only one equation in fluid mechanics, this is the equation you want to remember. Okay, so Reynolds number. If you take any class fluid mechanics heat transfer, you know, if you graduate from these classes, if you talk to people, you don't know what Reynolds number is, maybe they will laugh at you. Okay, so it's important to memorize this. Velocity times the length divided by viscosity. That's a definition for Reynolds number. Okay, I have 5 minutes. Let's go through a quick example. Try to talk to you about some of the principles. Okay, so look at example 5.1. This is a pipe, but it's a expansion, right? They call it diffuser, which means the diameter increases. So flow going into this diffuser. Okay, you have two regions, entrance 1 at outlet 2. Okay, so what did it say? A water 20-degree flow into, okay, mass flow rate Okay, do you know mass flow rate? I think chemical engineer, you guys probably know it, yeah, right, in other courses. The rate of the transport of the mass, right, kilogram per second, okay? Mass flow rate, usually we use m dot to represent the mass flow rate. Is that right? You understand mass flow rate, right?
Yes, sir.
That's what we use.
Yes, yes. Okay. Let's see. Section 1, the diameter. D1 is 3 centimeter. D2 is what? Doubled? 7 centimeter? Okay. Okay. So determine the increase in static pressure between section 1 and the section 2. Okay. So I need to actually give you the equation for the Bernoulli equation, okay, in order to solve this. You know, this is really need a fluid mechanics as a prerequisite for this, but anyway, it's a co-requisite now, so I have to cover it here. So Bernoulli equation is to calculate the pressure increase, okay? So basically it says P1 plus half rho V1 square equals P2 plus half rho V2 square in this problem. Elevation, we don't care, okay? Usually Bernoulli should have the elevation there, but let's assume the 2 point in the middle elevation is the same. So he asks you basically what is the pressure increase? So P2 is higher, right? So P2 minus P1 equals what? That's what actually the question is, okay? So from this Bernoulli equation, we know, okay, P2 minus P1 pressure increase equals to half rho V1 square minus V2 square. Is that right? From this equation, easy. Okay, so what do we really need to find out in order to calculate the pressure increase P2 minus P1? We just need to find out the V1 and the V2, right? From this equation. Is that what we want to find out? Okay, so anybody can help me find out the velocities? Since you guys know what the mass flow rate is. Anybody? Seems like you're not that confident, huh? Okay, doesn't matter. I'm out of time. I don't want to wait anymore. Mass flow rate equals to the area, the density times the area times the velocity. Okay, that's the equation for mass flow rate, right? Look at the units. Kilogram per cubic meter times meter square, right? And that's meter per second. So meter cancel, meter square. So it becomes kilogram per second. So that's the equation for mass flow rate. Okay, does that make sense, everybody? Mass flow, if you don't know mass flow rate, just remember this. This is the amount of mass goes through per time, okay? So this is the equation. So the principle is conservation mass. So mass flow rate at 1 should be equals to mass flow rate at 2. Your mass flow rate won't change, okay? The velocity changes, but your mass flow rate won't change. So that's the conservation mass from fluids. So basically it's rho A1 V1 will be equals to rho A2 equals to V2 equals to a kilogram per second. Okay, now can you calculate the V1, V2? Because you know A1 and A2, right? Do you? These are circles, right? Pipes. It's give you the diameter. What is area? In terms of diameter? Quarter pi d square. Okay, so you should be able to find A1, A2. Density is given, it's water, 1,000. So you should be able to calculate the V1 and the V2 based on the mass flow rate equal to 8 kilogram per second. Okay, so V1 is 11.32 meter per second, and the V2 is 2.079 meter per second. Then you can replace this V1, V2 into this Bernoulli equation. You should be able to calculate the pressure increase. 61.91 kilopascal, okay, kPa. That's the final answer. Okay, I'm kind of out of time. Any question? I can enjoy one question maybe. I can entertain one question if you want, if you have.
What was V2 again?
The velocity at the outlet. Okay, well, assume the one velocity, the inlet, one velocity, outlet. V1 is inlet velocity, V2 is outlet velocity.
No, I mean the value.
Oh, let's see, 2.079.
Thank
Okay.
you.
You're welcome. Okay, I guess that's it for today. Let's continue next time for the heat transfer part. Okay. Okay, have a good day.